Now, I don't have autopilot or full self-driving on my car. As a cost thing, it seemed like kind of a luxury to have it. I'm still interested in it, and I would still love to have autopilot on my Tesla. And at some point, I may still pony up the 3K and get it. But for now, I don't have it. But that doesn't mean that I'm not interested in it. It doesn't mean that I'm not keeping up with the trends there. And in fact, I'm really intrigued by the way they use artificial intelligence, or AI, to control the car and how that works, and some of the neural networks that they use to kind of process all the data that comes in. And one of the cool things about the car is it has a number of different sensors around the outside of it. I believe the number is 8, but I'm not positive about that. It might be more than that. But it has a number of sensors that use LiDAR, and that's a light-emitting, light-activated sensor. And it actually uses that to help with its some of the understanding of where things are around the car. So that's some of the proximity sensors and so forth that it uses. And in the original version of autopilot and of the full self-driving, they use LiDAR primarily to manage how the car drives and what it sees around it. Now, they do supplement it with some of the camera inputs. Now, recently I've read that Tesla was going to go away from the LiDAR completely and move to fully camera-operated sort of understanding of what's happening around it. And my first thought was, could that be right? Could they actually do that? And I was doing a little more research and trying to understand how that worked. And it kind of struck me that that was kind of an intriguing thing. And then I realized, well, maybe the cars don't actually use LiDAR and people are misunderstanding it. And it struck me that maybe I was not understanding exactly what was happening there. But then, as luck would have it, I happened to catch a live stream of an event where they were talking about some different automation improvements in electric cars. And one of the people that they had on was Andrej Karpathy. He's the lead AI person at Tesla. And he had about a 30-minute talk he did about why they're switching from LiDAR to cameras. And I thought, this is really fascinating, and this is really what it's all about. And now that I have that understanding, I wanted to share it with you. So I'm going to put some clips in here of him talking and let you understand what the concept is too. I'm just going to condense it down to the essentials so you kind of get the context of it. 30 minutes is a long time to sit through, but it's kind of neat.
People are not very good at driving. They get into a lot of trouble and accidents. They don't want to drive. And also, in terms of economics, we are involving people in transportation. And of course, we'd like to automate transportation and really reap the benefits of that automation in society. So we all, I think, are on the same page that it should be possible to replace the meat computer with a silicon computer and get a lot of benefits out of it in terms of safety and convenience and economics. So in particular, silicon computers have significantly lower latencies. They have 360-degree situational awareness. They are fully attentive and never check their Instagram, and alleviate all of the issues that I presented. And so I think this is not super shocking, and a lot of people have been kind of really looking forward to this kind of a feature. This is a frame from iRobot, a really good movie if you haven't seen it. And here, Will Smith is about to drive a car manually, and this other person here is shocked that this is going to happen. This is ridiculous. Like, why would you actually have a human driving cars? And so I think this is not very far from truth, and this movie is taking place in 2035. So I think by then, I actually think this is a pretty prescient prediction. The team is working primarily on the FSD functionality, which is our full self-driving suite. So here we have the FSD beta product, and it's in the hands of about 2,000 customers. And this is an example from one of the customers driving around San Francisco. And these people are posting videos on YouTube, so you can check out a lot of videos. But what we're showing here on the instrument cluster is we're showing all of our predictions. So you're seeing some road edges, some lines, some objects, and the car, of course, is navigating around autonomously here in San Francisco environment. Now, we, of course, drive this extensively as engineers, so it's actually fairly routine for us to have zero intervention drives, I would say, in like sparsely populated areas like Palo Alto and so on. I would say we definitely struggle a lot more in very adversarial environments like San Francisco. A lot of people working in autonomy, of course, know all about that as well. So this drive ends up being a fairly long drive, and it's zero interventions in this case. Now, one thing I like to point out always whenever I show the video of Tesla driving around autonomously in these city environments is you've seen this before, and you've seen it for a decade or more. So here's a Waymo taking a left at an intersection. And this is actually a pretty old video, I believe. And so you've been seeing stuff like this for a very long time. So what is the big deal? Why is this impressive? And so on. And I think the important thing to realize, and that I like to always stress, is that even though these two scenarios look the same, so there's a car taking a left at an intersection, under the hood, and in terms of the scalability of the system, things are incredibly different. So in particular, a lot of the competing approaches in the industry take this LiDAR plus HD map approach. And so the idea is that you take an expensive sensor, a LiDAR, on the top of the car, and it basically gives you range finding around the vehicle in 360 and gives you a point cloud. And what you have to do is you have to pre-map the environment with the LiDAR sensor, and you have to create a high definition map. And then you have to insert all of the lanes and how they connect and all the traffic lights and where they are. And you basically have to create a high definition map. And then at test time, you are simply localizing to that map to drive around. And so the approach we take is vision-based primarily. So everything that happens for the first time there in the car based on the videos from the 8 cameras that surround the car. And so we come to an intersection for the very first time, and we have to figure out where are the lanes, how do they connect, where are the traffic lights, which ones are relevant, what traffic lights control what lanes. Everything is happening at that time on that car, and we don't have too much high definition sort of information at all. So actually 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in this tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically like vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and is so much better, then the other sensor is actually starting to like really contribute. It's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar and how we have released this quite successfully so far to the fleet and what it has sort of taken for us to do that. So we prefer to just focus all of our infrastructure and development on this, and we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples. There's actually a massive difference between using radar at test time and using it in the offline tracker. And that is that at test time, a radar can just report a stationary track immediately in front of you, and you have 20 milliseconds to decide if you're going to brake or not. If you're offline, you have the benefit of hindsight. And so you can do a much better job of calmly fusing if you really want to. And so there is a massive difference there. And in addition, you can, of course, involve humans, and they can do cleaning, verification, editing, and so on. What this is, but basically this car drops a bunch of debris on us, and we maintain a consistent track for the label. And of course, if you have millions of labels like this, the neural net, if it's a powerful enough neural net, will actually end up learning to persist these tracks in these kinds of scenarios. Here's another example. There's a car in front of us. And I actually am not 100% sure what happens in this case, but as you'll see, there's some kind of a dust cloud that develops here and briefly occludes the car. But in the auto labeling tool, we are able to persist this track because we saw it before and we saw it after, so we can actually stitch it up and use it as a training set for the neural net. Here's one more example of an adversarial scenario from heavy snow. Again, we can auto-label this fine and create a large collection of examples. Right, is where you begin. You have some seed data set. You train your neural network on your data set, and you deploy the neural network in the customer cars in shadow mode. And the network is silently making predictions. And then you have to have some mechanisms for sourcing inaccuracies of the neural net. So you're just looking at its predictions. And then you're using one of these triggers, like I described. You're getting these scenarios where the network is probably misbehaving in extremely hard, diverse clips. And these are videos. So these are, you should roughly think about, say, 10-second clips, 36 FPS, something like that. In total, we have about 6 billion objects labeled cleanly for depth and velocity, and this takes up roughly 1.5 petabytes. So we've invested a lot into the compute. In this case, we have here a data set, we have a cluster that we're just building that is 720 nodes of 8x A100s of the 80 gigabyte version. So this is a massive supercomputer. I actually believe that in terms of flops, this is roughly number 5 supercomputer in the world. So this is actually a fairly significant computer here. We have 10 petabytes of hot tier NVMe storage, and it's also an incredibly fast storage. So I believe 1.6 terabytes per second. This is one of the world's fastest file systems. We own the vehicle and the sensing, and we source our own data, and we annotate our own data, and we train in our on-prem cluster. And then we deploy all of the neural networks that we train on our in-house developed chip. So we have the FSD computer here that has 2 SoCs, FSD chips here, and they have our own custom NPU, neural processing unit here, at roughly 36 TOPS each. And so these chips are specifically designed for the neural networks that we want to run for FSD applications. So the first example here, I have a video where this is on track testing. So this is an engineering car, and we asked it to slam on the brakes as hard as it possibly can. So this is a very harsh braking here in front of us. Even though it doesn't look like that in the video, this is very harsh braking. So what you can see on the right here is you can see the outputs from the legacy stack, which had radar vision fusion, and from the new stack, which is vision alone in blue. So in the orange legacy stack, you can actually see these track drops here when the car was braking really harshly. And basically the issue is that the braking was so harsh that the radar stack that we have actually ended up not associating the car and dropping the track and then reinitializing it all the time. And so it's as if the vehicle disappeared and reappeared like 6 times during the period of this braking. And so this created a bunch of artifacts here, but we see that the new stack in blue is actually not subject to this behavior at all. It just gives a clean signal. In fact, here, there's no smoothing, I believe, on the blue signal here. This is the raw depth and velocity that comes out from the neural net. It's as if like the radar doesn't know that there's like a stationary car in front of you or if it's the bridge above. It cannot differentiate those two. So radar thinks that there might be something stationary in front, and it's just like looking for something in vision to tell it that it might be correct. And then we create a stationary target and brake. And so in this case, in the legacy vision predictions, which were already producing depth and velocity, but because we were using radar, the vision inaccuracies were being masked because your bar is only at radar association. Your bar is not at actual driving. And so the depth and velocity were not held up to a high enough bar. And so basically what happens is vision reports for a few frames, reports a slightly too negative velocity for the car. And then it associates to the stationary object. And the stack is like, oh, that must be the stationary thing. And then we brake. And so this, of course, is much cleaner. And you see that the new stack does not see this at all. And there's no slowdowns in this case.
Now, there's one more connection I wanted to share here, and that has to do with me personally and the fact that in college I took a class called Human Factors in Aviation. And this was kind of an interesting class that talked about pilots and their interaction with the aircraft and the autopilot feature in the aircraft and how that interaction works and how the pilots work and so forth. And there were a lot of discussions about topics related to that. But one of the early days in the class, the professor challenged us all in the class and said, okay, I want you all to basically prepare a hypothesis that you either are for or against autopilot and why. So it took time to actually sit there and figure out how autopilot worked and what it did and what it meant and all of these things that you didn't necessarily think about when you think about getting on an airplane. So we had to do a little research and figure out what autopilot was. And what I learned was in the early days of autopilot on an airplane, it was a very much mechanical control. Basically, all it did was control the flight, making sure that it stayed level, making sure that it stayed at the same altitude and stayed at the same speed. That was it. It grew into something else where it could actually navigate a little bit and control the tail a little and the wings a little to turn and move a little bit so it could actually stay on course. And then over time, it became a totally electrical component, electronic component, and then eventually a computer component, where now everything is computer controlled. And not only can it stay in level flight, it can take off and land the plane. Now, I'm no savant, I'm no sage when it comes to this stuff, but I could see that computers were coming into play, and as the evolution was happening, it was clear that computers were going to take over the planes. This is the early 1990s, and it was clear that's the direction it was headed based on the research and things that were going on. There wasn't any AI happening, but there was a lot of things happening that can control the planes a little differently than they had in the past. And AI was a concept that was in the future, so certainly it could have happened and did. So my premise was simply that computers could and should control the planes because they could do it better than humans could do it. There are certainly a lot of factors that happen when you're driving or when you're flying that you have to concentrate and focus on a lot of things. You need to keep your speed, altitude, make sure that you're doing the right things, that you're coming in at the right vectors and everything's working the way you think it should. So all of these things contribute to huge amounts of pilot error. And if you look at the history of flight, most of the significant crashes were due to human error. So if you could remove the human error, you could effectively make the planes more efficient and more effective. So the premise was simply, hey, what if we were 5 years in the future, beyond when the computers were there, and a human got inside the airplane and said, I'm going to fly the plane and I'm not going to let the computer do it? How would people react to that? So it's the same principle that applies here. You have a car that can drive itself. We're at that cusp of being there where the car can drive itself. And people question, oh, can the car do it? Will it be ready for it? And my answer is still the same, yes. And in 5 years' time, from whenever this actually becomes effective, would people still react the same way? Wow, why did I ever drive a car? And I would make that analogous to the idea of a stick shift in a car. You don't see stick shifts in cars anymore. People always wanted to control the car and have that complete control over it. But now that they're not there, people don't learn how to drive a stick shift. My kids certainly don't know how to drive a stick shift and probably never will. And does it really matter? They're probably better off not knowing how to drive a stick. And at some point, they won't need to know how to drive a car. Does it really matter? And that's the big picture here. So AI is the wave of the future, and I think this is a really intriguing thing with Tesla taking over and making it use the cameras instead of the LiDAR. This is going to be really big. He mentions a site that's called tesla.com/autopilotai. And if you go through it, you see that they're actually talking about the kinds of work they're doing. A lot of the things that he highlighted are shown in here about the autonomy and the things that they're doing. And they're accepting applications from people. If you're interested in working in the AI field and you have some pedigree already, you could certainly go there and help revolutionize driving by just applying online. Pretty cool.